No viewers yet. Oh, now there's one. We'll start in about a minute. In a few minutes, we'll discuss power series from section 11.8. But first, we'll look at some of those infinite series from chapter 11, section 7. Hey, we were looking at this one when class ended yesterday, and we're applying the root test. And now we want to take the limit of n factorial over n to the fourth. So n factorial is greater than or equal to n to the fourth for what values of n? Well, let's see. When n is 1, 1 is greater than or equal to 1 to the fourth. 2 factorial is 2, but 2 to the fourth is 16. So 3 factorial is 6. 3 to the fourth is 81. So not yet. When n is 4, 4 factorial is 24. 4 to the fourth is 256. So 5 factorial, 120. 5, are we at 5? Yeah, 5 to the fourth is 625. 6 factorial, 720. 6 to the fourth. I don't know, let's see. 36 squared, that's 900 plus 1080, and then 1160, 1260. Anyway, when you get to 7 factorial, I'm pretty sure that 7 factorial is bigger than 7 to the fourth. So n factorial is greater than or equal to n to the fourth for n greater than or equal to 7. So this limit then as n approaches infinity, is unbounded, it's infinite. So that means this series, by the root test, diverges. Diverges. Okay, the next one. The infinite series, the terms are the tangent of 1 over n. So have you had a chance to think about this particular one? I'll take that as no.
What is an alternating? Is it an alternating?
It's not alternating. Yeah, 1 over n gets, when n is 1, it's the tangent of 1, which is a positive number. And 1 over n gets closer to 0. Tangent of 0 is 0, but these 1 over n gets smaller, and tangent of a small positive number is positive. Yeah, so it's not alternating. Okay, I'm going to try the limit comparison test. Limit comparison test with the harmonic series, 1 over n. So remember what that says. If you have two series, a sub n and a series of a sub n terms and the series of b sub n terms, and if the limit of a sub n over b sub n is equal to a finite positive number, so I'll just say where c is between 0 and infinity, if you get this sort of limit, a finite positive number, then either both series converge or both diverge. That's what the limit comparison test says. So I'm going to compare it with this infinite series. The terms are 1 over n. We know that this one diverges. So if we take the limit of the ratio and get a finite positive number, then that will tell us that this one also diverges. Okay, so let's try that. The limit as n approaches infinity of tangent of 1 over n divided by 1 over n. This is our a sub n divided by b sub n. We could proceed using 1 over n, but it's a little bit awkward to always think of the input value as 1 over n. So just for convenience, let's assign t to be 1 over n. And then observe that as n approaches infinity, what does t approach? Zero. Yeah. So we can rewrite this limit by making those substitutions. The limit as t approaches 0 of the tangent of t divided by t. So are we all okay with that? Okay, then we'll do a couple of maneuvers. Whoops, t approaches 0, I mean. So tangent of t is sine of t divided by cosine of t, and then multiply that by 1 over t. And we'll rearrange this a little bit. So we will have the limit as t approaches 0 of sine of t over t times 1 over cosine of t. And you might remember from Calc 1, the limit of sine of t over t as t approaches 0. So that equals 1. And the limit of 1 over cosine of t as t approaches 0 also approaches 1 because cosine of 0 is 1. So this particular limit, the limit of sine of t over t as t approaches 0, is one of the more famous limits. You would use this limit when using the definition of derivative to find the derivative of the sine function. Okay, so the limit is 1 times 1 is 1. That is a finite positive number. So that means that this series diverges because the series that we compared it with diverges. We compared it with the harmonic series, which we know diverges. So the limit comparison test tells us that this series also diverges. Okay, the next example, the infinite series, the term 2 to the n. So any thoughts on this one? Whether you're online or in class?
Ratio? The ratio test?
Say again?
Ratio?
Oh, the ratio test?
Yeah.
That doesn't look very fun. You can try it. Okay, what if you just had the series of the 1 over n to the second terms?
P-series?
It converges because it's a p-series with p-value equal to 2, which is greater than 1. Right? If you just think of this series by itself, that one is a p-series. The p-value is 2. And for a p-series, if p is greater than 1, it converges. I did say that right earlier, didn't I? Converges. So this one converges. Convergent p-series. And then another series that is involved here is 1 over 2 to the n. What kind of series is this? It's a geometric series. You could also write the terms on this one. You could write them as 1/2 to the n. So the common ratio is 1/2, which means it also converges. So this is a convergent geometric series. And we have a property of series that we saw a few days ago. I'll just write it this way. If the series of a sub n terms and the series of b sub n terms are convergent, then the sum of the two, well, though if we have positive terms, which those have positive terms, then the sum of those can be written this way, and it also converges. Remember that? So that's all we needed to do on this one. Okay, let's go ahead and start section 8 on power series. A power series is a series of the form where the terms are c sub n times x to the exponent n, and n can start at 0 and go to infinity. And so the individual terms are c sub 0 plus c sub 1 times x plus c sub 2 times x squared, and so on, where x is a variable and c sub 0, c sub 1, and so on are the coefficients of the series. For each fixed value of x, the series, this power series, is a series of constants that can be tested for convergence and divergence. So a power series may converge for some values of x and diverge for other values of x. The sum of the series is a function f of x equals c sub 0 plus c sub 1 times x, and so on. And the domain of this infinite series is the set of all x for which the series converges. So I'll just make a comment about the sequence of partial sums. Each term in the sequence of partial sums is just a polynomial function because it has a finite number of terms in each of those terms in the sequence of partial sums. So let's write that down here. If the sequence of partial sums, if the terms are referred to as S sub n, then what's S sub n? Well, if n equals 0 is where we start, then c sub 0 plus c sub 1 times x, and so on, and c sub n times x to the n. So this partial sum is just a polynomial of degree n. Okay, moving on. If c sub n is equal to 1 for all n, then the power series is 1 plus x squared, and so on. It's just a geometric series which we know converges when the absolute value of x is less than 1, and it diverges when the absolute value of x is greater than or equal to 1. Okay, more generally, a series of the form where the terms are c sub n times the quantity x minus a to the n, and if you expand that out, you'll see the binomial x minus a raised to the various powers. This is referred to as a power series in the binomial x minus a, but it can also be called a power series centered at a, or a power series about a. Okay, there's a theorem that we'll want to remember. For a given power series, the terms are c sub n times x minus a to the n. There are only 3 possibilities. The series converges only when x equals a. That's the first possibility. So if x equals a, what does that mean? It means all of the terms are 0. The series converges for all x, that is, all real numbers. That's the second possibility. And then a third possibility is that there's an interval of finite length. There is a positive number, capital R, such that the series converges if the absolute value of x minus a is less than r, and diverges if the absolute value of x minus a is greater than r. Okay, so the number capital R in case 3 is called the radius of convergence of the power series, and the interval of convergence of a power series is the interval that consists of all values of x for which the series converges. So in case 1, the interval of convergence consists of a single point A. In case 2, the interval of convergence is the set of all real numbers, negative infinity to infinity. And then in case 3, there are 4 possibilities for the interval of convergence. We can have the open set, a minus r up to a plus r, but excluding the endpoints. Or we could include the right endpoint and exclude the left endpoint. A third possibility, include the left endpoint but exclude the right endpoint. And then the fourth possibility, both endpoints are included. Okay, the ratio test is usually used to determine the radius of convergence r, and then the endpoints of the interval of convergence must be tested by some other means, since the ratio test is inconclusive when the limit of the absolute value of the ratios equals 1. Okay, we'll do some examples, and most of the time we're going to use the ratio test. On occasion, it will be more convenient to use the root test, but we'll use the ratio test to help us determine the radius of convergence. So if you see a few examples, that might help clear things up. Okay, so the directions: find the radius of convergence and interval of convergence of each series. So in other words, we want to find all of the values of x for which this infinite series is convergent. So the ratio test And we have the absolute value of a sub n plus 1 over a sub n. So since we're taking the absolute values, we can ignore the negative 1 to the n. But we will want to put absolute values around x because x could possibly be positive or negative. So the ratio test will write in the numerator the absolute value of n plus 1 times x to the n plus 1 divided by n times x to the n. We're going to take the limit of this in a minute, but we'll simplify a little bit first. So we can rewrite this. We can think of this as n plus 1 over n times the absolute value of x. Because x to the n plus 1 divided by x to the n is just x. Okay, so when we take the limit of this, we want it to be less than 1. Right, this limit has to be less than 1 in order for the infinite series to converge. And for each individual x, this absolute value of x is not affected by n. The only thing that's affected by n is n plus 1 over n. So the limit of n plus 1 over n times the absolute value of x is how much? Well, the limit of n plus 1 over n is 1. So we get the absolute value of x is less than 1. The goal is to find all x for which this limit is less than 1. So if this limit is less than 1, we just take the limit of this, which is just the absolute value of x. Okay, to solve this inequality, if the absolute value of x is less than 1, well, that means negative 1 is less than x, which is less than 1. Okay, so the radius of convergence is just 1. The length of the interval is 2, so the radius of convergence is half of that. And then we still have a little bit more work to do. We have to individually test x equals negative 1 and x equals positive 1 in this to determine if they are part of the solution set. So we'll test when x equals negative 1 first and look at the resulting series. So when x is negative 1, we have negative 1 to the n again. But negative 1 to the n times negative 1 to the n is going to be positive 1 for all n, right? So this series becomes n. So what do we know about that series? It diverges. Yeah, we're just adding 1 plus 2 plus 3. So it diverges to infinity. We informally say that it's equal to infinity, but what we mean is that it diverges. So that means we exclude -1 from the interval of convergence. Exclude -1. Now let's test +1 for x. So we get this infinite series, n equals 1 to infinity. We still have -1 to the n times 1 to the n is just 1. Hey, what about this infinite series? Well, if we write out the first few terms, it oscillates back and forth, but it's oscillating out of control, right? So we start with -1, and then we add 2, and then we subtract 3, and then we add 4. Then we subtract 5, and we add 6, and so on. So it diverges. Okay, so the interval of convergence then is just -1 less than x, which is less than 1. So I'll just make a note down here. The interval of convergence in interval notation is parenthesis -1 comma 1 parenthesis. Okay, the next series, the terms are x to the n over 2n minus 1. N ranges from 1 to infinity. So we'll apply the ratio test again. So I'll try to be a little more formal. The limit as n approaches infinity of the ratio. So we have x to the n plus 1 over 2 times the quantity n plus 1 minus 1 is just 2n plus 1 when we simplify. And then divided by x to the n over 2n minus 1. Hey, when we simplify this, notice we're going to get a simplification. You want me to write it down, or just, do you know what it is? I'll write it in a little more detail. So we're going to have x to the n plus 1 over 2n plus 1 times 2n minus 1 over x to the n. And x to the n plus 1 divided by x to the n is just x. So we're going to get the absolute value of x again. And then the 2n minus 1 divided by 2n plus 1, which will always be positive, so we don't need it inside the absolute value. And we want this limit to be less than 1. Okay, the limit as n approaches infinity of 2n minus 1 over 2n plus 1 equals 1. So if you multiply, or if you divide the numerator by n and divide the denominator by n, that's equivalent to multiplying by 1. So you get 2 minus 1 over n divided by to plus 1 over n, and as n approaches infinity, that expression approaches 2 divided by 2, which is 1. Okay, so we get the value of the limit then is the absolute value of x less than 1 again, which means -1 is less than x, which is less than 1. Okay, so the radius of convergence is 1 again, but we have to test the endpoints individually. So we'll test x equals -1 to start with. And when we test x equals -1, -1 to the n divided by 2n minus 1. This is an alternating sequence. And note that absolute values, so like the term 1 over 2 times n plus 1 minus 1, that's less than the term that came before it. So I'm applying the alternating series test. And this is pretty obvious that in the first condition, b sub n plus 1 is less than or equal to b sub n. That's the first condition of the alternating series test. And also the limit of b sub n as n approaches infinity, the b sub n terms are 1 over 2n minus 1. The limit of that is 0. That satisfies the second condition of the alternating series test. So that means we're going to include -1 in the interval of convergence. Okay, so we just use the alternating series test, and both conditions are satisfied. Okay, now we have to test the other endpoint. Test x equals +1. So the terms are just 1 over 2n minus 1. Well, we've seen infinite series kind of like this, close enough. Do you remember what this one does? So when I see that 1 over 2n minus 1, I think that's pretty close. I mean, it's similar to 1 over n. And the infinite series of 1 over n diverges. So we can try the limit comparison test with the harmonic series 1 over n. So I'll squeeze that in. Limit comparison test. And I'm going to compare it with the harmonic series 1 over n. Okay, so the limit as n approaches infinity of 1 over 2n minus 1 over 1 over n. So this is the limit as n approaches infinity of n over 2n minus 1. And this limit is equal to a positive finite number 1/2. So the limit comparison test tells us that this series does the same thing as the harmonic series. So since the harmonic series diverges, and the limit of a sub n over b sub n is a positive finite number, this series also diverges. So that means we're excluding x equals 1. So remember what we're trying to do. We're trying to find the interval of convergence for this. So we found it. We're excluding 1 and including -1. So the interval of convergence is bracket -1, comma 1 parenthesis.
I don't understand why we had to do the limit comparison test when on our test for x equals -1, we had the same thing and it went to 0. But then here we had to and it went to 1/2. I don't get why we had to do 2 different tests.
Here we were testing all of the numbers between -1 and 1.
Okay.
And but then we tested the endpoints. That was a separate operation.
Right, but I don't understand because these are the same limit, like we used the same, except that here we used a different test.
Okay, so, well, okay, so I see. When x is -1, we have an alternating series. But when x is +1, we don't have an alternating series.
Okay.
So that's why we use the alternating series test up there. Does that make sense? Okay, let's work on the next example. So we have the infinite series. The terms are the binomial x minus 2 to the power n divided by n to the n. So this is a clear case where we should use the root test. So the nth root of, nth root of the absolute value of x minus 2 to the n over n to the n, we get the absolute value of x minus 2 over n. Okay, so we want to take the limit of this. Okay, we want this limit to be less than 1. Okay, so let's just think about this limit for any fixed value or any value x the limit of a fixed value x, the absolute value of that number x minus 2 divided by n, this is going to go to 0 for any value of x. So this limit is 0, which is less than 1. So what does that tell us? That tells us that the radius of convergence is infinite, and the interval of convergence is all real numbers. Okay, radius of convergence is infinity, and the interval of convergence is all real numbers. Hey, does that make sense? If you pick x to be any real number whatsoever, then the numerator is fixed and the denominator approaches infinity, so the limit will be 0, no matter what value of x you pick. Okay, let's move on to the next page. See how far we get on this one. Okay, the infinite series, the terms are negative 2x to the n divided by the square root of n plus 3, and n ranges from 0 to infinity. So let's apply the, I suppose you could do the root test or the ratio test, but I'll start out with the ratio test. So the limit as n approaches infinity of the absolute value of negative 2x to the n plus 1 over the square root of n plus 1 plus 4, or the square root of n plus 4. And then divided by negative 2x to the n over the square root of n plus 3. Okay, we'll simplify what's on the inside. Okay. What are we going to be left with? The square root of n plus 3 divided by the square root of n plus 4, we can bring that outside of the absolute value. And then we have the absolute value of negative 2x. Or just the absolute value of 2 times the absolute value of x. Okay, we want this limit to be less than 1. So the limit of the square root of n plus 3 over the square root of n plus 4 equals 1. And so the limit is 2 times the absolute value of x. So 2 times the absolute value of x is less than 1. Or the absolute value of x is less than 1/2. Removing the absolute value symbols, we get negative 1/2 less than x, which is less than positive 1/2. So what's the radius of convergence for this infinite series? One half. Yeah, the radius of convergence is 1/2. It's 1/2 the entire length of that interval. And then we have to determine if the endpoints are included. So we have less than a minute. If you just look at the series when x is negative 1/2, so we get negative 2 times negative 1/2, which is 1, positive 1. And so we have the infinite series. One over the square root of n plus 3. So what do you suppose happens for this one? So when you look at 1 over the square root of n plus 3, I think of comparing that with 1 over the square root of n, or 1 over n to the 1/2, which is a divergent series. We're out of time, so tomorrow we'll pick up from where we left off.